This video is going to introduce the concept of the next inference procedure, two-sample t-test for means. So this example is given and we are going to do the inference procedure together, and you're going to see how quickly this follows from everything we've been doing. Has the mean number of hours of that the Americans work in a week changed? One of the questions of the general survey asked respondents how many hours they work each week. Responses are shown below. They were recorded from 1975 for employed Americans and 2014. Now these are random samples, so this is sample information, so keep that in mind. These are the sample sizes N, and we are hoping that they represent all employed Americans. So as you guys can see, there's two samples. So I would write that down. Also, what you can see is it says mean. So this is a mean questions. It's two means. It's a mean question. And if it's a mean question, usually if we don't have sigma, which is the population standard deviation, we're going to use S in place of sigma. It's a T situation. So keep that in mind. So here we're going to label and organize our stuff. We're going to call 1975 N1, and we're going to call 2014 N2 for the sample size of 1975 and the sample size of 2014. Then we have the means. This is actually going to be X bar, and this is going to be S because those numbers are from the statistic from the sample. So this is going to be X bar 1 and S1, and this is going to be X bar 2 and S2. So remember, these are statistics because they come from the sample, not population parameters, okay? Do these data provide convincing evidence? So we know that this is a p-value at the alpha equals 0.05 significance level that there is a difference between the true mean number of working hours from 1975 to 2014 for Americans. So as you guys can see, we have the difference of the means. Okay, so we want to generalize about all means from all Americans. Sorry, the mean of all Americans working hours from 1975 to 2014. All right, so we are going to be doing a test because we need evidence, and this test means we're going to do phantoms because it has a T in it, test. And so this is actually going to be called a two-sample t-test. All right, let's do it. Population 1. I'm hoping you're realizing the overall population is all Americans who are employed. So all employed Americans in the year 1975. And population 2, will that be all employed Americans in the year 2014? Parameter 1, will that be mu? Remember, it's mean, so you use mu here and not p, mu sub 1. The mean number of work hours per week. Just take it right off of here, guys. If you're confused about the parameter, use the word right in the question. Mean number of work hours per week for the Americans in 1975. And mu2, let's use red. Mean, let's use the symbol mu2. The mean number of work hours per week for the Americans in 2014. Again, like at some point you could start to abbreviate. Just on the AP, you don't want to abbreviate where the person doesn't understand what you're even saying. So just be careful. Also, instead of using 1 and 2, we could have used subscripts 75 and 2014 or 1975 and 2014. All right, so we're done with the P step. That's for panic. Remember, phantoms, P for population and parameter. Now we're going to go to the H step for phantoms, hypotheses. So remember, you're using your sample information, X bar 1 and X bar 2, to generalize about the population mu1 and mu2, and the difference of the population means. So the null hypothesis, when you write it, you could either write it as mu1 equals mu2, or you could write mu1 minus mu2 equals 0. Either way, you're writing there is no difference between the mean number of work hours in the year 1975 to the year 2014 for Americans. So remember, the null is always no. HO means no. No difference between the two. And then there is a difference between the two. Okay. So we didn't do the HA. This still says null. So let's add HA. So this is HO. HA. There is a difference. Mu1 is not equal to mu2, or mu1 minus mu2 equals not equal to 0. There is a difference between the mean number of working hours for Americans in the 2 years. I think there's a difference because I'm sure it went up. Let's look back and see. Did it go up? Yep, it went up just based on the sample, but is it a significant difference, right? So we're done with P, we're done with H. Now we're going to go to assumptions. The assumptions or conditions are listed here. They're the same ones that we've been doing all year. You guys know that they're two samples, so random samples. Are they independent of each other? 10N1 is less than POP1, 10N2 is less than POP2. And just like for the confidence intervals, we have to check if the sample size is large enough, the central limit theorem is met. But if it's not large enough, you can look at the overall population. And if that's not met, you have to plot the data. So that's what this box is saying here. Plot the data if you have to. Okay, so let's check it above. Let's go back to the top. We are going to assume that these two samples are independent because they're two separate years. It says that they are random samples, so that's great. The sample sizes are both very large, 764 and 1501, so the central limit theorem will be met, and the sampling distributions will be approximately normal. So all of these are going to be met, and I'm just going to pause the video here and write in my assumptions. Okay, so I just completed the assumptions. It was a lot of writing, so let's just quickly look at what I have here. It's stated to be two random samples. Assume that these two are independent SRSs from their respective populations of interest. 10N1 was less than POP1. That we got 7640. That's less than all employed Americans in 1975. And 15,010 is less than all population of all Americans that are employed in 2014. And since the two sample sizes were very large, the CLT is met, and by the central limit theorem, the sampling distribution of X bar 1 and X bar 2 are both approximately normal, and thus the sampling distribution of the difference of the two X bars is also approximately normal. So now that all of these are met, we can proceed. What is the name of the procedure? It is a two-sample t-test, which we kind of already derived in the beginning of this video. Now remember, the formula for any test statistic from the formula sheet is statistic minus parameter over standard deviation or standard error of the statistic, depending on if it's deviation or error. Remember, for the one sample t-test for means, the formula was a t-test statistic. We used t instead of z. And remember, the statistic was x bar. The parameter was mu sub x bar, which equals mu. And then the standard deviation or the standard error of the statistic was the standard error of the mean, was sigma x bar, which was sigma over radical n. But if we didn't have sigma, we used s in its place, so it was s over radical n, okay? So here is the setup: x bar minus mu over s over radical n for the one sample interval. So what is it going to be for the two sample? It's going to be the same thing, but double, right? So the statistic, instead of one x bar, it's going to be two x bars. X bar 1 minus x bar 2 minus the parameter, instead of 1 mu, it's going to be 2 mu's. Mu 1 minus mu 2. But guess what? We're assuming that this equals 0 in the null. So this whole thing is going to drop out over the standard deviation of the two means. Now, I just want to refer you to the reference sheet for this piece. Okay, so as you can see here, we're on the mean section, and we have one sample, and then we have two samples for means. So remember the spread. If it's standard error, when we don't have sigma and we use s in its place, remember one mean we said it's s over radical n. So for two means, it's here. This formula here, combining the two random variables together. So let's go back and plug that into the denominator. We have s1 squared over n1 plus s2 squared over n2. Okay. So now down below we have the formula now that I showed you where it comes from. It's written right here in the box. And then the same thing with the degrees of freedom. We're going to use the calculator to calculate the exact degrees of freedom for this. So we're not necessarily going to write the degrees of freedom ourselves because it's easier to use the technology to estimate it. So now we're going to go back to our example and we're going to plug in our test statistic into our formula and we're going to get our t-score. So x bar 1 minus x bar 2. So x bar 1 was here, 38.97 minus x bar 2 was 41.91. That's the statistic, x bar 1 minus x bar 2. Okay, minus parameter. We said, remember, mu1 minus mu2 we're assuming equals 0. So you could just write minus 0, or you could just not write anything because it kind of drops out. Over the square root of s1 squared over n1. So s1 is here, 13.13 squared over n1, which was 764, plus s2 squared over n2. s2 is here, 14.35 squared over n2, 1501. So again, do we really want to do this by hand? Of course we don't. So now we're going to go to our calculator for help. Okay, so we're going to go over to stat, we're going to go over to tests, and we're going to find our 2 sample t-test, which is number 4. 2 sample t-tests. Choose it. If you have data in your list, you choose data. Otherwise, you choose stats. We're going to choose stats because we don't have data in our list. Our x bar 1, we're going to substitute in 38.97. Our S1, 13.13. And our sample size 1 was 764. Again, this was from the year 1975. Make sure this all looks good. Now our x bar 2, 41.91. S2, 14.35, and our N2, 1501. All right, and then we chose a not equal to sign because it just said different. Now, I just want to remind you guys, we do not pool for this. We never pool for means. We only pool for the 2 proportion z-test, which is that special case. So choose no, choose calculator, drop. Now we have our t-score. T equals negative 4.881. I just want to remind you guys, if this were a drawing, that would be the negative z-score, but the symmetrical area on the other side for the t-score, would be the positive t-score, 4.881. So the total p-value is the two-tailed p-value, which is right here underneath the t-score, 1.158 times 10 to the negative 6 p-value. We'll be careful. 1.158 times 10 to the negative 6. Make sure you don't forget that E means times 10 to the negative whatever it is after the E. So this is scientific notation for actually a pretty small number. It's 0.5 zeros, 1, 2, 3, 4, 5 zeros, and then 1158. Wow, that's really tiny. So is that less than 0.05? For sure. So what are we going to do? We're going to reject the null. And thus we are going to conclude that there is a significant difference between the mean number of working hours in the year 1975 versus the year 2014. So make a decision. That's the M step. Here's my sentence. Because my p-value of 0.00000451158 is indeed very small, I reject HO. Very small p-value, pretty much 0. Sentence in context. Thus, I can conclude that the mean number of working hours per week for employed Americans changed. In fact, it probably increased. Thus, I can conclude that the mean number of working hours for employed Americans changed significantly between the year 1975 and the year 2014. So this is such a small p-value that it is like really, really, really good evidence that there was a significant change between the two. Another thing you guys could do is run the draw instead of the calculate option. And if you do that for number 4, you're going to see the two-tailed area that I'm referring to here. Sorry, I have something in y equals. Let me clear it out and then we'll do it again. But you see that the picture is showing that there's like a non-existent p-value. It's so tiny. Here it is. Okay, so they're showing you that there's like no chance that this happened by chance. So because this happened for the reason, specifically the significant reason that there was indeed a change between the 2 years. That's it.